All right, everyone. Welcome to lesson 13 of Calculus 1. So now we've learned how to take the derivatives of several different types of functions, and there will be more functions to come. We'll learn how to take the derivatives of trig functions and things like that in the future lesson. But for now, what we're going to do is we're going to look at some things that we can do with the derivative. So we know how to compute some of them. Let's figure out how we can apply the derivative in certain instances. So the key thing to remember about derivatives is that they represent an instantaneous rate of change, not charge, change. There we go. So if you ever want to know how quickly a function is changing at any particular moment, you take the derivative of that function and then plug in the variable value that you are interested in. What we're going to do is we're going to look at a few examples of this. Our first example of this comes from economics with the concept of marginal cost. So don't worry if you haven't studied economics before or business or anything. I'll explain what all this means. So what is marginal cost? Well, let's say we have a function, c of n, and c of n represents the cost of producing n items. So suppose we have some sort of business and we want to know how much it's going to cost us to produce, say, 100 of whatever we're selling. Then we would plug in 100 to this function, and that would give us the amount that we would be spending to produce all of that. Now, let's say we wanted to up our production. Let's say we weren't satisfied with making 100 items. Let's say we wanted to know what it would cost to produce 101 items. What we could do is we could look at Cn plus 1 minus Cn, and that will be the cost of producing the n plus first item. So we look at the cost of producing, for example, 101 items, we take away the cost of producing the first 100, and we're just left with the cost of producing that last item right there. This is very similar to what marginal cost is. So marginal cost specifically is going to be the derivative of our cost function. So we have c prime of n. Now, technically, this is the limit as h goes to 0 of c of n plus h minus c of n divided by h. But the thing is that usually in the real world, we can only produce discrete or whole numbers of items. So we can't quite send h to 0, but what we could do is we can at least send h to 1. Rather than sending it to 0, we're at least going to send h to 1. So dividing by 1 here will get rid of this fraction, and then we end up with Cn plus 1 minus C of n. Now, what does this represent? So this is the marginal cost. And so C prime of n is approximately the cost of producing one more item after already making n items. And it turns out as long as your n value is large, these two right here, Cn plus 1 minus Cn and C prime of n, those tend to be very similar in size. So let's take a look at an example. Let's compute marginal cost. So let's say the cost of producing X items in a given situation is 10,000 plus 5x plus 0.01 x squared right here. All right, so this is the cost of producing X items. And notice that even if we produce 0 items, we're still going to end up paying $10,000 or whatever our currency unit is. And why would that be? Well, this is what's referred to as a startup cost. So typically, if we're going to begin some sort of business, we need to pay money up front to get the machines to produce our items, or to buy a building in which to do our business, or to buy equipment that we need. Whatever that is all going to be, we need to get that before we even begin producing any items at all. That's why even at zero, it's still going to cost something. All right, so this is our cost function. So let's check out what the marginal cost is. That's going to be C prime of X. And here we use our knowledge about the derivatives that we learned about before. So we do the derivative of this constant 10,000, that will give us 0. Then we do the derivative of 5x. Well, a constant times the variable's derivative is just whatever the constant is. And then we do the power rule here. So we bring 2 down here and lower the power by 1. So we have 0.02 and then x right here. Our marginal cost is 5 plus 0.02x. So let's say we already made 100 items and we want to make the 101st item here. We can approximate how much that will cost to make that item by plugging 100 into this. So we have 5 plus 0.02 times 100. Well, 0.02 times 100 is going to be 2, and then plus 5 will be 7. So to make this 101st item, it's going to be about 7 units of money. This is what marginal cost can end up telling us. Now, in addition to cost, there are other quantities of interest in economics and business. So for example, we can have R of N is the revenue, or how much money we bring in from N items here. Now, unlike the cost function, which usually has a constant here, the revenue usually doesn't have a constant, because you usually don't make any money or bring any money in from selling 0 things. So it's unlikely that a revenue function will end up having a constant value. And just like marginal cost, you could take the derivative of your revenue function, and that will be called marginal revenue. And similar to marginal cost, this tells us how much money we're going to bring in by selling just one more item when we've already sold 10, or N, excuse me. Now, that's how much money we bring in. But what we have to do, we have to bring in more money than we're spending, right? So ultimately, what you're trying to do in business is you're trying to maximize your profit function. Profit from N items. And remember, your profit is going to be your revenue minus your cost function right here. So it's how much money you bring in minus how much money you've had to spend to bring that money in. So for example, let's take a look at another example. Let's say we have the same cost function as before. So C of X will still be this. And then let's say we have a revenue function for selling X items of 6X plus 0.02 X squared. Notice how there isn't a constant here. So what I want to do here is I want to figure out what the revenue, or sorry, what the profit is. So P of X will be R of X minus C of X. So we're going to have 6X plus 0.02X squared minus 10,000 minus 5X minus 0.01X squared. So this is the revenue function minus the cost function. And when we do this, we have 6X minus 5X is X. We have minus 10,000. And then we have 0.2X squared minus 0.1X squared. So we have plus 0.01X squared. Now, just like revenue and cost, we can also have marginal profit. How much money do we stand to gain after costs of producing one more item? So we could look at P prime of X, marginal profit. And what will we get here? Well, we do the derivative of X and we get 1. We do the derivative of negative 10,000 and we get 0. and we do the derivative of 0.1x squared, that gets 0.02x here. So for example, if we want to estimate how much profit we will make by selling one item when we're already selling 100, we do 1 plus 0.02 times 100. These will again be 2, so we'll end up with 3. So even after taking costs into account, we'll be making $3 per item once we've already sold 100. Now that will probably be lower in the beginning. Businesses have a hard time making money when they first start out, but it seems like, at least according to these equations, the more money we make, or sorry, the more things we sell, the more profit we're going to get out of each individual item. Not just overall, but each individual item. So anyways, this is one application of the derivative to see how much cost, revenue, or profit you'll make from selling one more item in your business. All right, now I want to talk about another application, and some of you may have already been familiar with this. I mean, you may have already been familiar with the economics right here, but you probably have seen physics in high school. So that's going to be our next application here. So what we're going to do is we're going to explore one-dimensional motion. Okay, now what is that? The best way to imagine this is if you have like a train on a train track, which we're going to represent as a number line, and we can move either to the left or to the right, but not up or down or back and forth. So it's motion effectively along a number line. Okay. Now, what we're going to do first here is we're going to define a function called s of t. Now, s of t will be your position of your object or particle or whatever you want to call it at time t. So for example, if you start your stopwatch at t equals 0, then s of 0 will be your initial position on this number line. And then if you let the object move and then stop your watch at t equals 1 second later, you can plug in 1 into our function here, and then will be with the new location of your object. S of t is our position function right here. Now, in addition to knowing where something is, so like let's say the particle's right here, we also may want to know how fast this particle is moving. Now, the rate of change of position is going to be called velocity. This is the rate of change of position. Now, we see that these three words here, rate of change, that means that this is probably a derivative in some way. Anytime you see the words rate of change, you can probably express something as a derivative. And since this is the rate of change of our position function, that means that v is going to be s prime of t right here. So that's going to be our velocity, or how fast we're moving is going to be the derivative of our position function here. Okay, so let's take a look at an example here. So let's say I have a position function that looks like this: 4t minus t squared plus 4. This is my position function. And I want to know how fast and also in what direction this particle is moving at any given time. So that means I need to find my velocity function. My velocity function is none other than the derivative of the position. So I do the derivative of this, and now we know how to do this easily without using the limit definition. We do the derivative of 4t, and we get 4. We do the derivative of negative t squared, bring the 2 down, lower this to have negative 2t. And then we do the derivative of the constant 4, which will be 0. So our velocity is 4 minus 2t right here. So this tells us how fast we're going at any given time. Now let's take a look at v of 0. So typically when we plug 0 into something in physics, it's called the initial, whatever it is. So this will be the initial velocity in this case. If I plug in 0 into here, 4 minus 2 times 0 will be 4. So what this means is that at our time t equals 0, we're going to be moving at 4 units per second, and we're going to be moving in the positive direction. We're moving 4, so we're going to be going to the right here. Now, what about our initial position? Our initial position, we plug 0 and 0 in here, and we also get 4 for this. What does that 4 mean? If we go to this picture here, our little particle starts at a position of 4. And what it's doing right at the very start is it's moving this way at 4 units per second here. Okay, now, will that always be the case? Well, this doesn't have constant velocity. Like if I plug in t equals 1, for example, 4 minus 2 will be 2. So at t equals 1, it'll still be moving to the right. It's still a positive velocity, but it'll be going a bit more slowly than it was when it started. Okay, now let's say I plug in, say, I don't know, t equals 3 here. If I plug in t equals 3 in for my velocity, then I have 4 minus 2 times 3. That ends up being negative 2. So what does a negative velocity mean? It means that we're going to be heading to the left. And we're going to be heading to the left at a rate of 2 units, maybe it's meters or feet or something like that, per second or per time interval, whatever unit we select. So it seems like we can have both positive and negative velocity. It simply means the difference in signs means which way we'll be moving along our number line here. Okay, now I want to figure something out here. So I was kind of exploring what these meant here. I want to check something out. How far does the particle travel from t equals 0 to t equals 5? That's going to be my question here. Now, the thing is, you might be like, oh, this is a pretty easy question. I just see where it ended up, and then I subtract off where it started, and then the difference between that will be the distance. Now, if we were going in the same direction the whole time, that would be 100% accurate. That'd be totally true. But we notice here that when we start off, we're going one way, we're moving to the right. But then a few seconds later, still within this time interval here, we begin moving to the left. So we actually backtrack on our own progress. So we're actually going to go farther than s of 5 minus s of 0 would seem to tell us. So in order to figure this out, well, I mean, our answer is not going to be quite what it seems. What we need to do is we need to see which intervals we're going in which direction. And in order to do that, we set our velocity function equal to 0. So we're going to set our velocity equal to 0. Now, why do we set it equal to 0? Why do we actually do that here? It's because that the velocity can only change sign when it passes through 0, at least for most physical situations, which are continuous. So in order for it to go to the right and to the left, it needs to decelerate and stop moving to the right and then begin moving to the left. And that needs to happen, that switch happens when our velocity function is 0. So if we solve this equation for 0 here, we have 4 equals 2t, and then we end up with 2 equals t right here. So it seems like at t equals 2, that's when we're going to switch directions here. So what we're going to do, let's draw our number line here. So this is at t equals 0. So our particle starts here at 4, like we established earlier. What we need to do is we know it starts traveling to the right initially because our initial velocity is 4, and then it's going to stop moving to the right. Our velocity will be 0 at t equals 2. So it seems like we end up going this way until t equals 2. Now, what position are we at t equals 2? Okay, well, we have 4 times 2 minus 2 squared plus 4. All right, well, this is -4 plus 4 is 0, and then we have 8 here. So it seems like we start at t equals 4, and then at t equals 8, which I shouldn't have drawn that far, we come to a stop right there. Our velocity is currently 0, so at that instant, we're not moving at all. A particle goes like this for the first 2 seconds, and then what we do is we see the distance between these two. The distance between 4 and 8 is 4. Now, it's kind of obvious because I drew a picture here, but what if we didn't draw a picture? How would we figure out what this is? Well, we could look at the absolute value of s of 2 minus s of 0, and that would also give us 4. We want it to be absolute value to make sure this isn't a negative number if we headed to the left instead. So this is how much we went on the first leg of our trip. So t equals 0 to t equals 2. Now, t equals 2 seems to be the only place where our velocity is 0. So that means that this can only change directions at most once. Because if it needed to change directions again, it would need to pass through 0 again. So that means that once we get to t equals 2, we're going to go all the way to t equals 5, and we're going to be going to the left the whole time. So for the second leg of our journey, we'll do s of 5 minus s of 2. So let's see, we just established s of 2 was 8, and s of 5, let's see, 4 times 5 is 20, minus 5 squared, which is 25, is -5, plus 4 is -1. So we have -1 minus 8, which ends up being 9. So what we do is at t equals 2, we turn around and we go back this way all the way to -1 right here. So we go from 4 to 8, and then we go from 8 all the way back like this. So we add these two together, 4 plus 9, and we get 13 distance traveled. Whereas if we just did s of 5 minus s of 0, we would get just a distance of 5, but that's not quite what happened here. Now, there's another term in physics called displacement, which is simply your initial position minus your final position. If you want to figure out displacement rather than distance, then that would just be 5. But we want to know distance here. How far do we actually travel? Our distance is going to be 13. All right, now I want to introduce a new mathematical concept, and I'm going to do so using the physics right here. So notice that when we were moving here, our velocity also changed. So our initial velocity started as 4, and then it went to 0 at t equals 2, and then we saw it went negative afterwards. So it seems like our velocity is changing as well. So perhaps we may want to know what the rate of change of our velocity is. And there's a term for that. That's going to be a of t, which is acceleration, or the rate of change. You often see that abbreviated as ROC, of velocity. Okay, now once again, if we're the rate of change of something, that means that we can represent that as a derivative. So it seems like we are the derivative of velocity here with respect to time. Now, let's think about this for a moment. How did we define v all the way back here? V was also a derivative, so it was s prime of t. But now we're doing the derivative of v. So we can imagine this almost as like d dt of s prime of t, because s prime is v, and then we're doing another derivative. So if we do the derivative of something that already has a derivative, this is called the second derivative. And we write it in the way you'd probably expect. Instead of just putting one little tick mark there, or one prime symbol, we put 2. So you could say, in addition to being the derivative of velocity, acceleration is also the second derivative of position. And what this means is we do the derivative of position, and then we do its derivative again. This is how many times we consecutively take the derivative of a function. All right, well, we already computed what our velocity was for our example earlier. We already did that derivative, so we might as well use it here. Now let's see what our acceleration is. That's going to be v prime. And the derivative of 4, the constant, is 0. And the derivative of negative 2t will be negative 2. So it seems like our acceleration is constant in this case. So that means that our speed is always moving to the left. So the longer this particle moves, the faster and faster we'll be moving to the left. So maybe at like t equals 100, we'll be moving extremely quickly to the left here because our velocity is constantly getting more negative as time goes on. All right, now I want to draw all 3 of these as functions on a graph. And we already saw the relationship between the derivative, a function and its derivative on a graph. And then we could also put the second derivative in there as well. All right, so here is a graph of 4t minus t squared plus 4 here. So that's going to look like this. Oops, I'm gonna go the other way. There we go. So here's a graph of s of t. It's a downward facing parabola here. Let's see, 4t minus t squared plus 4. All right, and then our velocity function was 4 minus 2t. So 4 minus 2t will look something like this. All right, and then our acceleration will simply be a constant, a negative 2. Okay, now let's take a look at the relationship between these. So our position, it seems to be increasing at first. It pauses for a moment at t equals 2. This is where the velocity ends up being 0. And then it seems to go to the left or in the negative direction afterwards. So we notice here that our position is increasing until t equals 2. So the derivative is going to be positive until t equals 2. Because remember, the derivative is positive when a function is increasing, and then it's going to be negative while it's decreasing. So it's going to be negative once we get past there. And if we now look at the relationship between v and a, remember that a is the rate of change or derivative of v. Now, v is decreasing at a constant rate the whole time. It's just continuously sloping down and to the right. So since it's continuously decreasing at the same rate, we're going to be at this constant negative value of 2 right here. So this is all 3 of them plotted on the same graph right here. And at least for polynomials, the more derivatives you take, the lower the degree of the polynomial is going to be. So if you see something moving up and down a bunch of times, that's more likely to be the original function rather than a derivative. All right, now we don't need to have second derivatives just in the context of physics or motion of particles. We can also have higher derivatives just in pure mathematics as well with any kind of function that we want. And especially in calculus 2, we're going to be using a lot of these higher derivatives quite frequently. Let's take a look at an example here. Let's say that y is x cubed plus e to the 2x. What I want to do is I want to find the first 4 derivatives of this function. All right, and so we saw a second derivative earlier. We're going to actually go as far as 4 derivatives, and there's actually no real limit to the number of derivatives that you can take, so long as each function successively is differentiable. If we ever end up getting an absolute value in there, something like that, that might be a problem. But typically polynomials and exponential functions, those we won't run into trouble with. All right, let's do our first derivative. I do the power rule here for x cubed. That becomes 3x squared. And then I have e to a number times x. So that will mostly stay the same, except we put a copy of that number in front here. So I'm going to have 2e to the 2x. All right, that's our first derivative. Our second derivative, we simply take the derivative of what we just got again. So I do the power rule here, giving me 6x. And then I use the exponential rule again. I put another 2 in front. And the 2 times 2 will make a 4. Next, we have y triple prime here. I put 3 prime markers there. I have the derivative of 6x will be 6. And I bring another 2 down here to make 8 e to the 2x. And then finally, I'm going to do one more derivative. Now, it's customary after 3, if you want to express more derivatives than that, rather than writing a bunch of tick marks forever, we put an exponent with the number of derivatives, but we put it in parentheses to distinguish it from y to the 4th power. So this would be how we would write the 4th derivative of y with a parenthesis and then a 4 here. Now, if we do this final derivative, the derivative of 6 will be 0, so this polynomial is completely decayed away, and we bring another 2 down here. We have 16 e to the 2x. So what this goes to show is that over time, if you take enough derivatives of some functions, namely polynomials, they will go to 0 overall. But there are some functions like exponential functions and other functions we'll see later that no matter how many derivatives you take, they'll never disappear, although they may change every time we do a derivative. All right, that's it for this lesson. So in the next lesson, we'll be learning how to find more derivatives of more functions here. So I will see you guys then.